Hi, I'm Rodini Sampaio from PARG Research Group in Fortaleza, Brazil. I'll talk about target set selection with maximum activation time. This is a joint work with Lucas Kyler, Carlos Vinicius, and Carol Maia from Fortaleza, Brazil, and Ignazi Sal from Montpellier. In the target set selection model, TSS model for short, is given a graph G in a threshold function tau, which associates a number to each vertex of the graph. The threshold of any vertex, tau of v, is at least 1 and at most d, the degree of the vertex, as defined by Chen in 2009. In an activation process of a TSS model, g tau, it is also given a subset S0 of vertices, which are considered active at the beginning, and the other vertices are inactive. If a vertex V is inactive and has tau of V active neighbors, tau of V is the threshold of V, then the vertex V is activated. This is an irreversible process. Active vertices remain active forever, and the process is synchronous. All inactive vertices update their status at the same time in each step of the process. Here we have an example, the graph G. The thresholds are the numbers in red. We have only one vertex with threshold 2, the other vertices have threshold 1. The black vertices are the vertices of S0, activated at the beginning. Time 0, the activation time is the number inside the vertex. This vertex has threshold 1, then is activated at time 1. Also this is activated time 2, time 3, time 4. This is activated time 2, this is activated time 3, but this vertex is not activated time 4 since the threshold is 2. This vertex is activated time 5, and then this vertex is activated at time 6. S0 is a target set if all vertices are activated at the end of the process, and the activation time is the maximum activation time among the vertices of the graph. The activation time of the graph G is the maximum activation time among the target sets of the graph. Okay, so S0 is a target set if all vertices are active at the end. Thresholds are at least 1 and at most the degree of the vertex as defined by Chen in 2009. The classical target set selection problem, the TSS size problem, is the problem of finding a target set with minimum size. There are many recent works investigating the TSS size problem, which is linear time solvable in trees and APX hard. In our work, we introduce the problem TSS time, find a target set with maximum activation time instead of minimum size. In this example, this target set with 2 vertices is the minimum target set and also obtain the maximum activation time. But this is not always happen. The TSS time decision problem, it is given a graph G, a threshold function tau, and an integer t. Is there a target set as 0 with activation time at least t? Since it's a maximization problem, the decision problem is at least t. Some examples, this is the same graph. This is the same graph with same thresholds, but the minimum target set with 2 vertices obtain the maximum activation time, but this target set with 5 vertices also obtain the maximum time 6, maximum activation time 6. These are the 2 examples, same graph, same thresholds. This is the only vertex with threshold 3 is the minimum target set with activation time 5. And this target set with 11 vertices obtain a maximum activation time 10, which is better than 5. TSS time results in the literature. This problem was posed by Bolabas in the square grid with all thresholds equal to 2. When all thresholds are equal to R, the TSS model is called R neighbor bootstrap percolation. When all thresholds are 2, it is called P3 convexity, and the target set is called a house set. The exact value on the hypercube was obtained in 2012. It was proved that this problem is polynomial time solvable in the square grid when all thresholds are 2. And the decision problem is polynomial time solvable for time 3 in general graphs and time 4 in bipartite graphs when all thresholds are 2. Okay, we can also generalize this problem, GTSS time problem, generalized TSS problem, which comes from generalized TSS model. The thresholds may be 0 or greater than the degree. Vertices with threshold 0 are activated at time at most 1, and vertices with threshold greater than the degree must be in any target set, since they cannot be activated by its neighbors. For example, these 3 vertices have degree 1 and threshold 2. Then they must be in the target set. Any target set, they must be activated at the beginning. These 3 vertices have threshold 0. They are activated at time 1 alone. Okay, some results on the GTSS time problem. G from generalized, we allow threshold 0 or greater than the degree when all thresholds are equal to 2. It was proved in 2014 that this problem is NP complete for time t at least 4 fixed in general graphs and time 5 in bipartite graphs, and all thresholds are 2. And it was proved that it is W1 hard on parameterized by the true width. Hardness results on GTSS time do not apply directly to TSS time, since most of these hardness reductions use many vertices of degree 1, which is not allowed when all thresholds are 2 in TSS time, but GTSS time is okay. Vertices of degree 1 in these reductions are very important to control the activation process. Okay, so our results. We proved that TSS time is linear time solvable in trees. GTSS time is quadratic time solvable in trees. We obtained several hardness results on the TSS time problem. And we proved that this dichotomy, TSS and GTSS time in minor closed graph class C are FPT on parameterized by the time t and tau star, which is the maximum threshold in the graph, if the graph class C has bounded local true width. Otherwise, they are NP complete for any fixed time t at least 4 and tau star equal to 2. In 2011, Benzui showed that the parameter true width governs the complexity of the TSS size problem, the classical target set selection problem. Our conclusion is that the parameter local true width governs the complexity of TSS time and GTSS time problems. So, our result on bounded local true width. Let n at most t of V be the t neighborhood of V, the vertices at distance at most t from V. So if G has bounded local true width, we have that the subgraph induced by the t neighborhood of any vertex V has bounded true width for any fixed t in any vertex V. So if the maximum activation time of a graph G is at least t, then there is a vertex V in a target set S0 such that S0 activates the vertex V at time at least t. If we include all vertices at distance at least t from V, these vertices cannot decrease the activation time of V. So we have this, and this implies that there is a vertex V such that the maximum activation time in the graph induced by the t neighborhood of V is at least t. For fixed t and tau star, we obtain, tau star is the maximum threshold, we obtain a monadic second order formula for TSS time, which implies that this problem is FPT parameterized by the true width. This implies from this that TSS time is FPT in bounded local true width graphs parameterized by t, the time t, and tau star, the maximum degree. Now our result, our NP hardness result in Hypix graph. An Hypix graph is a graph which can be made planar by removing a vertex when all thresholds are exactly equal to 2. It is based on a paper of Benevides, Campos, Dourado, Sampaio Silva in 2015. Is a reduction from restricted planar trisat, which has clauses with 2 or 3 literals. Each positive literal appears twice, each negative literal appears once, and the variable clause graph is planar. For every clause with 3 literals, we build this gadget below. This represents the 3 literals. For every clause with 2 literals, we build the gadget below. These 2 vertices represent the 2 literals of the gadget. Observe that one of these vertices must be in any target set, in a target set, in any target set, since the threshold is 2 and they have only one neighbor outside the set. So all other vertices cannot activate these 3 vertices, okay? So suppose we have this vertex in this example. So with this, one of these 2 must be in any target set. This is activated at time 1, which activates this in time 2, since this is 0. It's activated at the beginning. This is also activated time 2. This is activated time 3, activated time 3. So this is activated time 3, and this is activated at time 3. The same happens, similar thing, when the clause have 2 literals. So this is an example with 3 clauses x or y bar, and x bar or y. So each clause is a vertex in this graph, and each variable is a vertex. We join the vertex with a clause if the vertex is in that clause. Okay, so the variable gadget, the variable clause graph is planar. Then replacing the vertex, the clause vertex by the gadget, we also have a planar graph. By replacing x by 2 vertices, x bar, 2 vertices x bar, and 2 vertices y bar, we have only one y bar here, so we join with this vertex. Only one x bar here, we join with this vertex. We can make this graph planar. Okay? We include a vertex z, joining all these vertices, the variable and its complement, and we also include this gadget here. So we proved that all these vertices are activated in the gadget. Closed gadgets are activated time at most 3. So these vertices 2 with 2 activate this vertex in time 3. Okay, so all these vertices are activated time 3. This means that the vertex z is activated at time 4, at most 4. Okay, the vertex chosen in these gadgets represent the true literal in the gadget. So in this case, we have x true and y true, which satisfies all clauses. This assignment. Okay. So the vertex z is the only one with activation time 4, since this vertex 1 helps to activate him. But if we chose this vertex 0, for example, time 0 activated at the beginning, we would have time 1 here, and then this vertex with this vertex, we would have time 2 in this vertex xy bar, and then z would be activated time 3. So if the formula is satisfiable, we prove that z is activated time 4. Otherwise, z is activated time 3. And we prove that it is NP-complete in APX hard. Why APX hard? Because removing the vertex z, the graph is planar, as we can see from this. Okay, so how we prove now that local derivative governs the problem TSS time? Theorem. The TSS time problem in a minor closed graph class C is FPT on T and tau star if C has bounded local truth. Otherwise, it is NP complete for n fixed T at least 4 and tau star equal to 2. From Epstein to 1000, let C be a minor closed graph class, then C has bounded local truth if and only if C does not contain all apex graphs. If the graph has bounded local truth, then we saw that it is the TSS time problem is FPT on T and tau star. Otherwise, it contains all apex graphs, and we saw that it is NP complete for any fixed time T at least 4 and tau star equal to 2. Okay, this is our dichotomy. Other result is polynomial time algorithms in trees. A vertex V in a tree is saturated if the threshold is equal to its degree. Here we have an example. This vertex has threshold 2 and degree 2. We prove that the maximum activation time is the size of a maximum path with non-saturated vertices plus 1. We have this path of non-saturated vertices, these green vertices. Okay, these green vertices are non-saturated vertices. This is the maximum path with non-saturated vertices plus 1. We prove that the path can always end at a saturated path, a saturated vertex. So we have plus 1 here. So this path has 17 vertices plus 1, 18. We could also show that in this other direction, we obtain the same thing, the same time, 18. Okay, and GTSS time in trees. Now we have the generalized version. We allow vertices with threshold 0 and vertices with threshold greater than the degree. We first simulate the activation process from the forced vertices, the vertices which must belong to any target set, and including the vertices, the activation process with the vertices with threshold 0, the activation process ends activate some vertices. For example, all these vertices are activated at the beginning with these forced vertices. Now, we can prove that by selecting some vertices, we prove that the maximum activation time is the maximum among paths P of non-saturated and inactive vertices of the size P of the path plus the beginning time of P plus 1. In this example, the beginning time of this path of non-saturated vertices, the beginning time is 7. So we have 7 plus 1, 2, 3, 4, 5, 6, 7, 8, 7 plus 8, 15 plus 1, 16. 16 is the maximum activation time of this graph. We prove that it is solvable in O of n squared time. And we have another example here. We could have in other direction, but the activation time is smaller. Okay, that's it. Thank you very much.